Hey guys, welcome back to another video. I know I haven't uploaded in quite a while, but we're back. Alright, so in this video we're going to talk about linear regression, which is probably one of the most basic machine learning algorithms that you can learn. And while it might seem boring compared to some of the more modern models, it's certainly quite important that you have a good grasp and understanding on how linear regression works in order to understand the more complicated and difficult models. Alright, so yeah, also it's a good stepping stone into machine learning in general. Okay, so let's get started. On my screen I have a scatter plot of data points, right? And the data points show on the x-axis we have the house size, and the y-axis we have the house price. So what this means is that given a house size, we can see how much it costs, right? For example, this one, I can see how much it costs, right? And then this green line fits all the data points in a linear fashion, and we call this line the hypothesis function. And this is basically linear regression, right? Fitting a line to the data. Okay, so what does this line actually tell us? Why do we need this line? So, for example, if we know how much a house, how big a house is, right? The house size, we can simply do this. For example, we know how big it is. We can draw up to here, and we can get a data point here. And then, since we know this, we know how much it costs, right? So this is the y value. You know, we have the x value of the line, we can get the y value, which is the house price. So this is a good way to predict how much a house will cost based on the house size, right? Given a house size, we can predict how much it will cost, right? You know, we can predict it for any house size, right? We can do it here, you know, we might have one here, right? It's super useful. And it's not going to be a perfect estimation, right? It's still a good estimation, right? For example, this one, it's not perfectly accurate, but yeah, it's useful. Now let's move on to the mathematics behind how this actually works. Alright, so here's the general formula for linear regression, and you can see here that is the hypothesis function, right, that we talked about earlier. And you know, we have theta and x. So you might be wondering, what is theta and what is x? Well, x is what we call features in this case. So what are features? Well, features are fairly simple. You know, house size is a feature, right? The number of rooms in a house, that's a feature. Number of fans, number of swimming pools, you know, you get the point. Those are features, right? And so since, wait, let me write it out real quick. These are features, right? X and the x values are features, and all right, we get that. So what are theta? What is theta then? You know, what are these? Well, actually, before we get to that, x0 is actually generally written. X0 is always 1, actually. So in practice, we don't actually have to write out x0. I'm just writing it to show you how you can write it to better understand, right? And so theta is what we call feature weights, right? So what are feature weights? Well, feature weights are what machine learning is actually trying to learn from, right? The better the feature weights, the more accurate the model will be, right? So that's where machine learning comes in. And this term here, this is called the bias term. Let me write it out. Bias term. And you can just disregard x0 since it's just 1, so it doesn't really matter, right? And these are the features. X are features. Yeah, okay. So now we got that out of the way. I will talk about how you can optimize for data later. We will use a technique called gradient descent, which requires calculus. So if you're not familiar with differentiation, partial derivatives, I highly suggest you to learn those first before you learn gradient descent, right? So, all right, let's move on. So here is the simple linear regression. You might see this a lot from a lot of YouTube videos. So what this is, it's really simple. It's if I write it this way, you might see it more clearly. This is basically the same thing as y equal mx plus b or c, depending on where you're from. And so, right, it's just the equation for a line, right? Theta 1 here is m, x1 here is x, theta 0 is b or c, depending on where you are, right? This is just the line, the equation for the line. And theta, and x1 here, in our example, it's, our example back here, it's actually the house size, right? House size. So it's something that we can use to estimate how much the house will cost, right? Cool. All right. Let's see. Yeah, I think that's about it. And we can also express this formula up here in vectorized form. So what do I mean by that? Here's what I mean by that. So we can express data as a vector containing values from x0 all the way to xn, and then x values all the way from x0 to xn as well, right? X as vectors. And then we can just do the dot product of data and x, vectors. And it's basically the same thing as theta 0 times x0, theta 1 times x1, theta 2 times x2, and all the way up to theta n times xn. So yeah, that's pretty easy to understand, right? Remember that this is called the hypothesis function. All right, cool. And if you're wondering how can I implement this in Python, you can use the NumPy library. You can just do np dot and theta x, right? So it's fairly simple to implement if you're actually looking forward to implementing this. All right, cool. Now we got that done. And now let's move on to how do we actually maximize, how do we optimize our linear model, right? So, we got the same data, same scatter plot here, except you see that I added some white lines over here. So what are those lines? Well, those lines are called residuals. Let me write that down. Residuals. So what are residuals? Well, residual is basically the difference between the predicted value and the actual value. So in this case, the predicted value is this point on the green line, right? That's what we predicted based on the house size for the house price, right? And then the actual value, the actual house price, and we subtract that from the predicted value, and that's how we calculate the residuals, right? But yeah, we use something called a cost function, or you can call it loss function. Doesn't really matter here. And what cost functions are used for is evaluate model, right? Evaluate model. All right, cool, fantastic. yeah, you can also call it loss function. It doesn't really matter. Cost, loss function. Alright, so how do we do that? Well, in this case, we use a cost function called means. Actually, let me do that in a different color. I feel like that's better. We use a cost function called mean squared error, right? And it's pretty self-explanatory. It's basically the mean of the sum of the error, and the error in this case is you'll see when I write down the formula. So 1 over 2m times the sum and I equal 1, and then predicted value minus right. So let me explain what this formula is. So we're taking the sum of y hat here. It means the predicted value, and we're taking the ith predicted value starting from 1 all the way to m data points, and then we're squaring that difference. So why do we square that difference? Well, number one, it can get rid of negative signs, right? We don't want negative signs because it can cancel out, right, between data points here. So it's not good to have negative points. And so you might ask, why don't we just take the absolute value then? Well, you'll see later on that we do this for a lot of different reasons. One of them being that it's easier to, well, it's a lot easier to take the derivative of a function squared instead of absolute value, right? If we take the derivative of this, we just bring 2 to the front. And that's why we wrote a 2 here. We don't actually include 2 typically. Well, we do this so that it's easier to take the derivative of this function, right? It just cancels out. But normally it's just the mean of the sum of the squared errors, right? But we added 2 here, so it's easier to cancel this out later on. So yeah, that's mean squared error. And let's see what else. Okay, let's define this as j theta 0, theta 1. Alright. Let's see. Well, you can also actually write it this way technically. You can express y hat as h of the hypothesis function, right? And we're taking the ith hypothesis function. That's also a good way to write it, right? Since we're plugging in x, we get the y predicted value anyways. So that's another way that you can express it. Okay, all right. Now you might also see a cost function called root mean square error, right? So what's the difference between mean square error and root mean square error? Well, root mean square error is pretty self-explanatory. It's actually just square root of mean squared error. So why do we take the square root of that? Well, if we look back at our scatter plot here and we use the mean square error, we can see that the unit we get at the end is house price squared because we squared here, right? And it wouldn't really make sense, right? It's a unit that doesn't really make sense. House price squared, right? That's not really a good indicator. So that's why we take the square root. So now the unit is house price, right? I feel like that's much more explainable, right? But in practice, we actually don't need to use root mean square error when optimizing the machine learning model, because taking the square root of this and using this is the same thing, right? We're trying to minimize this. Yeah, sorry, I forgot to mention, we're trying to minimize the cost function because, we're trying to get the least amount of error in terms of the difference between predicted values and actual values, right? So we're trying to minimize it. And if we're trying to minimize this, it's basically the same thing as minimizing this. So it doesn't really matter in this case. Alright, so now let's see, how do we actually optimize this line here? How do we get the best data values so that our function, our cost functions are minimized, right? So that's called something, well, we're going to work with something called gradient descent, right? So let's see. Oops, sorry, my bad. Alright, so we're optimizing theta, right? And we're using gradient descent. Sorry, let me move this out the way. One sec. Alright. So yeah, we're using something called gradient descent. And if you took calculus, you know that gradient is similar to the slope, right? And descent means going downward, and so it means slope going downward. And I'll explain later why this term makes a lot of sense, right? So what is the gradient descent used for? So here I have theta 0. If you don't remember what theta 0 is, let me go back up. Oh, by the way, I'm doing this for simple linear regression, this model here, right? So we only have theta 0 and theta 1, right? We know x1 because, we have house size, right? So we're good with that. And we're trying to optimize theta 0 here, right? So, how do we get this curve, right? So we got this curve by plugging in different values for theta 0, right? We might have a value here, and then we get this value for mean square error, right? So by plugging different values for theta 0, we get different mean square error or different cost function values, right? So what's the best theta 0 then, you might ask? Well, since we're trying to minimize mean square error, the best theta 0 value will be here, right, at the bottom of this curve, right? And that will be the best theta 0, the one that we're trying to get, right? Since mean square error is the lowest here, so it'll make sense that we're trying to optimize for this. Alright, so how do we actually do that? Well, we use something called gradient descent. So let's see how that works. For example, let's start at theta 0 equals 0, right? So this point. And then what we do is that we jump down here. We gradually jump down here to this point and, to this theta 0 value. And then we do it again. But this time we're taking smaller steps. And gradient descent does this through mathematics, right? We'll see how this works. And then take smaller steps, all the way until we reach this point, right? And then if it goes further, it will just realize, hey, wait, this point was lower, and so it wouldn't make sense. Yeah, so that's what we do here. And x0 is also the intercept, so we're optimizing for the best intercept value here. And how do we actually mathematically use gradient descent? Well, let me show you. Here, we can just move here. Yeah, I feel like that's better. we actually take the partial derivative of the function j, right? If you remember j, theta 0, theta 1, right? J is the cost function here, right? Remember, this is the cost function, mean square, and theta 0 is the intercept, or the intercept value, and then theta 1 is the feature weight, right? We're optimizing for these. Okay, so then how do we so let's first optimize theta 0. So that's what we're working with. So what we do is we take the partial derivative j over partial derivative theta 0, and that's equal to partial derivative. Let me write it out first. It's easier this way, and then we write down our cost function 2m sum I equal 1, then theta 0 plus theta 1 x1 xi minus yi square, right? But yeah, this is basically I'm using xi here because we're plug in the x value, the ith x value, right? And then the ith y value. So we take the partial derivative of this, and then what we get is we move 2 to the front, right? So 2 cancel out, and then it's just divided by m. Okay. So I believe that would be 1 over m times I equal 1, and then since theta 0 is actually not multiplied by anything, we can just actually wait, hold on, let me think for a second. It's either this or maybe we don't write the 1 over m. Yeah, I'm not really sure for this, but maybe we don't write this. If you have taken partial derivatives, you can correct me here, but I don't think we take it. I don't think we should include it. Maybe we should, I'm not sure, but yeah. And then theta 0 plus theta 1 xi minus yi, and since the 2 cancel out, we don't have to write that, and we multiply by 1, which is the same as not multiplying by anything. So why do we multiply by 1? Well, since 1 here is multiplied by theta 0, so it's not shown, and then that's why we multiply by 1 here. Alright, then we do something called step size. So how do we get a better theta 0 value? Well, we take the old theta 0 value, and then we use gradient descent, right? We multiply by something called learning rate. We multiply something called learning rate by what we just wrote, the partial derivative, right? And if you're wondering what learning rate is, it's basically a factor that determines how big of a step that you should take. We typically start pretty big, like 0.1, 0.001, depending on it really depends, but yeah, in practice we start big, and then gradient descent will optimize it. And oh sorry, I didn't mean to cross that. So by doing this, we go down further and further, right? Alright, cool. And then the learning rate gets smaller as slope gets less steep, right? And actually this whole thing is called the step size. Alright, cool. And now we actually do the same thing for data 1 as well, doing all these steps. And we do it all the way until we reach the best value where mean square error is minimized, right? Now, what are some problems that we can run into? Well, let me show you here. Let me start a new graph. Well, we can run into problems where it's something called a local minima, right? So, our graph doesn't have to necessarily look like this, right? It almost never looks exactly like that. And we might have something like this, right? So then we have two minimas, right? This is called the local minima. This is called the global minima, which is the lowest point, but this is the local lowest point you can think of, right? And then, with MSE on the side, data 0 or data 1 doesn't really matter here. So for linear regression, you actually optimize for all the data using gradient descent, right? For the partial derivative, you can double check on this, but I could be wrong here, so correct me if I'm wrong in the comments. Thank you for that. Right, so how do we solve this issue? Well, one of the things that we can do is we try different values, right? Instead, we can start somewhere like here instead of starting at theta 0 equals 0, right? Or theta 1 equals 0. Right, we can try random numbers to start with, or we can change the step size, right? Larger step size, we could skip over the minimum, right? We can actually jump over it to avoid it. And the thing is that the larger the step size, the more inaccurate it is. While the smaller the step size, the more accurate it is. But it takes longer time to optimize, right? Yeah. So what are other things that we can use? Well, we can also use a concept called stochastic gradient descent, which takes random points and then it basically picks a random, well, not here, but sorry about that. It takes a random data point, right? And then it calculates the derivative at that point, and then it calculates the new values, right? And yeah, so this avoids, this causes randomness, which makes it more likely that we're able to find the global minimum, right? And you can also use something called mini batch stochastic gradient descent, which takes a group of points instead of a single point here, right? Yeah, it's super useful. So the special thing about gradient descent is that we don't actually have to use, the special thing about linear regression is that we don't actually have to use gradient descent, right? We can also use something called the normal equation. So what is the normal equation? Let me write it out. Normal equation. So what does this do? Well, let me write out theta equal x transpose x 1 x transpose y. Right, so sorry, not calculating. So what does this do? Well, what it does is that it's a formula that we can plug in to find the best data value, right? And so why don't we just use this instead of gradient descent, right? Well, this actually works really well for smaller data sets you can use this for smaller data sets, but as the data set gets a lot larger, it will become it will take a long time to calculate. So that's why we use gradient descent in practice. But yeah, some interview questions might ask you on this, but generally they will ask you on gradient descent, right? And the normal equation only works for linear regression, by the way. You probably won't see it anywhere else for machine learning, right? And yeah, x here is just independent variables, and y is the dependent variable, or the value we're trying to predict. X could be, you know, house price, house size, number of swimming pools, etc. So now, how do we? I only showed you how we can solve for the simple linear regression, right? Simple linear regression, we only have one feature, right? So what if we have like two features, for example? Then we run into something called multiple linear regression. And let me write that down. So multiple linear regression, instead we use a 3D plane, right? Now it could be number of rooms. Add arrows here so you can see house size, and then we're trying to predict the house price, right? So then you know, let me add some data points. I'm gonna make it larger to indicate that it's closer, and then smaller as it gets further, right? So how do we optimize for this? Well, instead of a line here, we actually have like a plane. Oh god, that's terrible. I'm sorry. Yeah, we have a plane here to best measure, to best predict the values, right? And this is called multiple linear regression, right? All right, so, and that's with two or more values, and if we only have one feature, then it's just called simple linear regression. Yeah, and if we have more than two values, we can't actually graphically display this, so that's why I'm only showing you with two. But yeah, it's the same thing. We use gradient descent to optimize for all of them, right? You know, it's just more features. You know, it could be theta 3. We just optimize for theta 3 using gradient descent. And yeah, I feel like that's really it. Yeah. Alright, cool. I think that's it for this video. If you enjoy this, please subscribe. I'm going to make more videos like this on whiteboard explaining things later. Or maybe should I do animations? What do you guys think? Maybe whiteboard it's easier to explain things, or maybe animations. You guys decide in the comments below. Alright, thank you for watching this video. See you next time. Bye.